Hi, welcome back, and we are starting to dive into interactions that deal with fluids instead of just dealing with solid objects. And in doing so, we had to define this idea of pressure, and with this idea of pressure, we were able to understand and utilize Pascal's principle, which helps us build devices like hydraulics. Now, in understanding the behavior of fluids, important questions such as why do objects float come into play, where we are now looking at interfaces between solids and liquids. We are still in this realm of hydrostatic forces and hydrostatic behavior, that is to say, stationary fluids, but now we are going to start to look at interfaces between objects and fluids that are maybe submerged in those objects. So goal for today, define and derive the buoyant force. A single goal, but that's not to say this is going to be a short video because the derivation is a little bit longer and it's going to take us a little bit of time to get through it. So buckle up and let's go ahead and get into it. When we look at an object that is submerged in a fluid, let's take some water here, put maybe a cube inside of the water. We ask the question, well, what forces are acting on this object? Perhaps this object floats, in which case we have some downward force due to gravity pulling it downward, but if it's floating, if it's stationary at that location, that must mean there's an upward force. What is that upward force? Well, it's not a normal force, right? It's not resting on a surface. It is instead a buoyant force. A buoyant force is the force that a fluid exerts in an object that is submerged inside of it. Well, what is that buoyant force? Where does it come from? To understand where it comes from, we take a look at this cube and we zoom way in, right? We're going to zoom way into perhaps the bottom surface of this cube. And on the bottom surface, we have the molecules of the cube themselves, whatever the cube is made out of, molecules. And then we also have inside of the fluid molecules that make up the fluid as well. And these molecules that make up the fluid are more free to move. In fact, they move around quite rapidly. And as they move around, it is likely that they are going to hit the surface of the cube and bounce off of it. And during that collision with the cube, an impulse is had, and there are countless number of molecules colliding with the cube, giving us countless impulses, each of these impulses exerting a force that is upwards. So we have some upward force acting on this cube on the bottom surface. And that's not all, because when we look at the side of the cube, again, we have all of these molecules bouncing off the side of the cube. That means that there's some rightward force from the molecules colliding with the left face of the cube. And there's a leftward force from the molecules colliding with the right of the cube. And in fact, there's even a downward force from the molecules on top of the cube colliding with the top of the cube. So we get these forces that are occurring in every direction caused by this buoyant force. Well, we then ask the question, how can we calculate, how can we quantify that force? And to quantify that force, we go back to this idea of pressure. We say the pressure, which is acting on the bottom of the cube, well, that's just the hydrostatic pressure from the molecules of water or whatever fluid we're looking at. The molecules on the left-hand side of the cube, well, that's going to be due to the pressure of the water on the left-hand side of the cube. And on the top of the cube, that's due to the pressure on the top of the cube, the hydrostatic pressure. So in each of these, we have to use this idea of hydrostatic pressure, which can be calculated as rho GH, right? Well, rho GH plus atmospheric pressure, right? Because we have to add on the fact that there exists air above the surface of this fluid. And, interestingly enough, we'll see that that atmospheric pressure is not actually going to play a role here. But we'll include it for right now. Okay. So, moving on, right? We have our cube. Our cube is submerged in water. I'm going to redraw it here in 3 dimensions. And we are going to first analyze the pressure on each of the sides, not top and bottom, of the cube. When we look at the right-hand side, we have pressure that is exerting a force to the right. If we look at the right-hand side, we have pressure that's exerting a force to the left. If we look at the back of the cube, we have pressure exerting a force forward. And if we look at the front face of the cube, we have a pressure exerting a force backwards. So we have forces going in every direction here. But there is no reason to believe there are any more or less molecules on any side of the cube. And there's no reason to believe that the collisions are any more violent on the right or left side of the cube, so there shouldn't be any more force that is imparted on the right and left side of the cube. So when we look at the forces, we might say that each of these four forces, are equal in magnitude. Equal in magnitude, but in the case of each of these pairs that I outlined in blue, opposite in direction. And if that is the case, then we can say that each of those forces acting on the cube are going to cancel each other out. Each of those forces that I've outlined in this picture cancel each other out. Meaning that the net force, which is a combination of all of the forces acting on this cube, the net force is going to be given from the force that is acting on the top of the cube and the force that is acting on the bottom of the cube. And there's a negative out front of the top. Why? Because the force on the top is downwards. So I'll rewrite that just to clarify. Equals to negative. And then we have, of course, near the Earth's surface, we have weight mg. And we say, okay, well, looking at this, we said earlier that the net force is going to be caused by the buoyant force in the weight, meaning that this force on the top and force on the bottom, that must be our buoyant force. The buoyant force must be the force on the bottom, and I'll spell out the whole word bottom, minus the force on the top of the cube from the fluid. So that is our buoyant force. Okay. Now we ask the question, well, how the heck do we find this? How do we figure out what the buoyant force is going to be? So erase this cube. We know the left, right, front, and back faces aren't going to do anything, so it's only the top and the bottom that we have to worry about. We start off with the example. Here's a container, and our container will have some fluid line, and I'll do a better job of drawing that. Our container has some fluid level filled with fluid. So we're going to put an object into this fluid. We submerge an object into the fluid, and I'm going to just draw a square, but this could be any object. It could be a cube, it could be a cylinder. We're going to look at a cube, and it might be more correct to draw out the cube as three-dimensional. I am just going to look at it as though we're the profile of the cube. Why did I do that? I do that to keep things a little bit cleaner. When we look at the top of the cube, we say, well, this level is at the top of the cube. At that level, there will be a pressure equal to the density times G times the height of the top of the cube. And this is essentially the depth of the cube, right? So rho G H top. And if we look at the bottom of the cube, a little bit deeper, and the pressure at the bottom of the cube is going to be rho G times H bottom. So we have the height at the top, we have the height at the bottom. At each of these, we get different pressures. I'll put HB, HT to differentiate those two. But we get different pressures. And we know the force is related to the pressure by the definition of pressure being force over area. Which means if I wanted to know the force at the top of the cube, well, the force at the top of the cube is going to be the pressure at the top times the area of the top of the cube. And for the sake of this problem, I'm just going to write A here for area because the top and the bottom of our cube are going to have the same area. Likewise, the force at the bottom of the cube is going to be the pressure at the bottom, PB, times A. And taking these definitions, replacing force on the bottom of our buoyant force and force at the top, we arrive at the equation. I'm going to write it over here to the left. That the buoyant force, spelling it all out here, is equal to the pressure at the bottom times the area minus the pressure at the top times the area. And we see, okay, well, each of these terms has an area, so I'm going to swap out, or I'm going to remove that area and put it outside a fraction to give me this equation. And we look at this and we say, well, pressure at the bottom, that's going to be rho g h bottom. Rho g h bottom. Pressure on the top, well, that's going to be rho g h top times the area. And I look at this and I say, well, both of those terms has the density of the fluid. That doesn't change, right? We're considering here a incompressible fluid, although, again, it does work with compressible fluids, but density does not change. Acceleration due to gravity, that's always 9.8. So instead, we can write this as h bottom minus h top times rho g area. And where does this lead us? Well, let's take a look at our cube, right? If we take a look at our cube, this orange line will represent h bottom, right? The height to the bottom of the cube. If I subtract off this red line representing the height to the top of the cube, well, what's left on our orange bar is just that bit. And that bit is the same height of the cube itself, right? The same height of the cube itself, which I will represent with the letter capital H being the height of the cube. So we take the total height to the bottom of the cube to the surface, we subtract off the top of the cube to the surface. What we're left with here is the height of the cube itself, which means we rewrite this as, I'm going to use density times acceleration due to gravity out front, multiplied by that newfound height times the area. But wait a second. The area of the bottom and top face of the cube multiplied by the height, area times height, that is by definition the volume of this cube. So I could even go so far as to erase height and area and replace it with the volume of the cube. And I'm going to put volume OBJ for volume of the object. In fact, maybe I'll spell that out. So the buoyant force, therefore, seems to be density times acceleration due to gravity times the volume of the object that is submerged. And when we take a look at this, I glossed over an important aspect. For both of these pressures, we would actually have the addition of atmospheric pressure. But since we're subtracting the two, the atmospheric pressure cancels out. So just in case you had that question, where did atmospheric pressure go? It actually cancels out here. Because both pressure terms have it, we're subtracting one pressure term from the other, so we end up canceling out our atmospheric pressure. We're just left with rho g times the volume of the object for a submerged object. But this does beg the question, what if your object's not totally submerged? What if, for example, we had a container here where our object is not completely submerged, rather it's floating with only some partial submersion. Let's say we are only submerged some smaller part, where that smaller part we can call volume submerged. We find the total volume submerged. And this buoyant force, well, it's no longer rho g times the volume of the object. Instead, how we would write it is that the buoyant force is more accurately written as density of the fluid we are submerged in. Not the object, but the density of the fluid that the object is submerged in, times acceleration due to gravity, times not the volume of the object, but the volume of the object that is submerged. And this is what is known as Archimedes' principle, that the buoyant force depends not on the mass of the object, rather it just depends on how much of that object is submerged, as well as the density of the fluid, but it doesn't depend on the mass of the object. And this is interesting. This is interesting because when we take a look at this, we say, well, I know that massive objects tend to sink, right? If I take a block of lead and a block of wood, the block of lead that is more massive will sink and the block of wood will not. So why is that the case? Why does it seem like this doesn't match up with our intuition? And to understand that, I am going to take a look at an object that is floating. When we have an object that is floating, we have a buoyant force and a gravitational force. And what is important here is that the buoyant force is equal to the weight if our object is floating. If the weight were larger, it would sink. So this is the requisite statement for an object that is floating. And when we take a look at this, we say, well, it's going to be the density of the fluid multiplied by the acceleration due to gravity multiplied by the volume submerged. And that must equal the weight of the object, which is mass times acceleration due to gravity. Right off the bat, we see G cancels out. So we say, okay, well, that's the density of the fluid, and I'll shorten that subscript to rho FL, times the volume submerged. And that's equal to your mass, but I'm going to write my mass a little bit differently. I'm going to write it as density of the object times the volume of the object. And when we look at this, we can rearrange some terms. Perhaps I will want to relate the densities of our two objects. Density of fluid is equal to density of object multiplied by the volume of the object over the volume that is submerged. And when we think about this, well, the volume of the object, if we are floating, the volume of the object must always be greater than the volume that is submerged. You can't submerge more of an object than there is volume of object itself. And if that's the case, then for our object to be floating, the density of the fluid must be greater than the density of the object, right? Because this fraction is going to be less than 1 always when our object is floating. And if our object is floating, well, then that means that our fluid must have a larger density than our object. So we think of an object that floats, and what's important is not that it's less massive than an object that sinks. Rather, what's important is the comparison between the density of the object and the density of the fluid. And this gives us our relationship for an object that floats. Well, what if it sinks? If our object is sinking, that just means the density of the object is larger than the density of the fluid. Okay, so I know this was a little bit longer of a video. I know it came out to be about 20 minutes, but this is a very important concept. This is a very important idea, and it blends together a lot of the past stuff that we were doing when it comes to statics. This idea that in equilibrium, we can compare buoyant forces and weights. We will have some problem-solving practice posted for you in another video. If you have any questions, please be sure to reach out. Otherwise, I will see you guys in the next video.